So today we are going to talk about basic derivative rules. Now, if you'll remember, up until this point, we have used, right? This is still the definition of the derivative. The limit is h approaches 0 of f of x plus h minus f of x all over h. This is still the rule, but the good news is that there are lots of rules out there that make it possible for us to not use this procedure every time, okay? And so we can use these particular rules when we're dealing with nice, smooth, continuous places, okay? So the first one is the constant rule, and this is saying that the derivative of any constant is equal to 0. So let's just do an example of that, just so that you get an idea. So first of all, we have to remember that the derivative is a rate of change, and if a function is constant, then it's really not changing at all. But just in case, let's say that our f of x is equal to c, okay? So we are going to apply this rule straightforward. So that means I'm going to have the limit as h approaches 0 of, okay, so when I go to put in x plus h into here, I have no x. So my top really just becomes c minus c because this is c, but there's no place to put in an x plus h, so I just get c minus c over h, which is just 0 over h without even doing the limit. And so my derivative here is 0. So if you think about it, again, remember, the derivative is a rate of change, right? And any graph that is in the y is equal to c is not changing, right? It's a horizontal line. And so the rate of change is 0. So the derivative of any constant is equal to 0. So for instance, if I had the derivative of, if I was doing the derivative of x with respect to x and I just had 7, then this is 0. So as long as I just have a number, then the derivative of a number is 0 because it's a constant, it's not changing at all. So that's our first rule. All right, so this is the life-changing one. Okay, so we call this one the power rule, at least for derivatives. So if n is a rational number, meaning my exponent is rational, then the function f of x equals x to the n is differentiable, meaning I can find the derivative of it at any point, right? This is kind of a polynomial. And the derivative of x to the n, this is the great thing, is n times x to the n minus 1. And so what ends up happening is we multiply the power out in front, right? The n came down and sits in front, and we subtract 1 from the power. Right? So let's use this. So this is, right, this is x cubed, and so if I was going to attempt the limit as x approaches, or h approaches 0 of f of x minus f of x plus h minus f of x, then the first thing that I'm going to need to do is put in x plus h here and cube it, okay? So that's like 4 terms, right? You're going to get x cubed plus 3x squared h plus 3xh squared, and so forth and so on. And so this is not really a fun process, especially when you get over an x squared. And so this nice power rule says that what we can do is that f prime of x, now you notice I didn't say equals here, right? I don't want to say this is equal because this is something completely different. It's related to f, but it's completely different, so it's not equal. So f prime of x is equal to, okay, so I'm going to, this says 3 is my n, so I'm going to have a 3x to the 3 minus 1 power. So to simplify that, that means that f prime of x is equal to 3x squared. All right. If you don't believe that this works, go back and look at all those ones that we did using the limit and apply the rule and see if your value matches. All right, so this allows us to do things like this as well first, except there's a rewrite that we need to do first, okay? So in order to use our power rule, I need to have it written as x to the n power. And rational means it can also be a fraction. So the first thing I'm going to do is rewrite g. So this could be written as x to the, remember it's power over root. The implied power on x is 1, so that's my numerator. And the root is 3, so I get x to the 1/3. So my g prime then is, okay, so this time my n is a third. It's still rational. So this is 1/3 x to the 1/3 minus 1. So I want to simplify this to g prime of x is equal to 1/3 x to the negative 2/3. Because I'm going to subtract, I want change 1 into 3 over 3, and I get 1 minus 3 in the top, which is negative 2/3. All right, oops, so this is my g prime. G prime is 1/3 x to the negative 2/3. All right, so we can do the same thing here. Again, I need to write it. I can't do the derivative of x in the bottom. It has to look like this, x to the n, not 1 over x to the n. So the first thing I need to do is rewrite m. M of x is equal to x to the, right, I can pull anything out of the denominator. I just apply a negative power, right? That means that's the reciprocal. And so now my m prime of x is pulling the exponent, multiplying it in front, negative 2, x to the negative 2 minus 1, which gives me m prime of x is negative 2, x to the minus 3. Right, so much easier, right? Okay. Now there's a special case of a power rule that I just kind of wanted to point out. This actually still works the same way. It's just that I have x to the first, right? So if I think of it like this, then if I have x to the first, then what I'm going to use my power rule. Remember, my power rule says the derivative of x to the n is n times x to the n minus 1. So I multiply the 1 in front, and then I get x to the 1 minus 1. So I end up with 1x to the 0. And anything to the 0 power is actually 1. So I end up with the derivative of x is equal to 1. Okay. This applies to any linear type thing. And the reason why, so let me just show that the derivative of 7x is the same. It would be 7. It's just the number in front. And that's because if you think about it, right, again, think rate of change, right? And when I'm dealing with something that looks like this, then I'm dealing with a linear function. And linear functions, their rate of change is constant, right? It's always the slope. And so when I'm taking the derivative of a term that's just x, then I want to think of it as, right, I mean, if I graphed this, it would look like, it should be quite steep, right? It should look something like this because it's got a positive 7 slope. Well, anywhere I choose on here, right, it's the same rate of change. It's exactly, the slope is constant. And so the rate of change of 7x is just 7, okay? All right, so that's a special case of the power rule. So let's use it now. So if you recall, when we were finding equations of a line tangent to a function, right, the first thing we had to do was apply that limit process, okay, but now it's much simpler, right? Again, my equation of a tangent line requires a point and a slope. And so the first thing I could do is find my y value, and I find y by just plugging in x, right? So f of 1 is 1 to the 4th, which is still 1. So I have the point 1, 1. So my equation of my tangent line looks like this so far. Y minus 1 is equal to x minus 1, and then this is the derivative, f prime at 1. Okay? All right, so now I just need to figure out what f prime of 1 is. So I can find f prime very quickly now that I don't have to use my limit process. So f prime of x first, right? So my exponent is 4. I bring it down. I get x to the 4 minus 1, which is 3, and there's my derivative. So then f prime of 1 is 4. I pop that in and I'm finished. So I get y minus 1 is equal to 4 times x minus 1, the equation of my tangent line. Isn't that so much easier? All right. Now we can extend the power rule. So all of the ones that I did so far, I just had x to a power to what we call the constant multiplier rule. So if f is a differentiable function, right, that I can find the derivative of everywhere, and c is just a real number, then if I multiply that constant by my original function f, right, it's also differentiable because it's just a constant, and the derivative of the with the constant times the function is just the constant times the derivative. Okay, so I'm going to prove this one because it's a really quick, easy proof. So I'm going to go back to my limit as h approaches 0 of f of x plus h minus f of x all over h. And we're going to use y equals c times f of x. All right, so we're going to apply this literally. So I'm going to plug this in. The limit as h approaches 0 of, okay, so first I plug in x plus h. I'm just going to write it like this. So I have c times f of x plus h minus c times f of x, because that's my original function. Okay, and so I'm going to then divide by h. Now I have this c, which is common to both things in the numerator, which means I can factor it out. Okay, so I'm going to have the limit as h approaches c, or I'm sorry, 0. I pull out the c, and in the top I get f of x plus h minus f of x over h. And so this c, right, when I'm doing a limit and I have this constant here that's completely unaffected by h, then I can actually write it out in front. So I can write c times the limit as h approaches 0 of f of x plus h minus f of x over h. And this is our exact definition of what f prime of x is. So this is just c times f prime of x. All right, so that's just a very simple proof. All right, so now that we've kind of gone through all the rules, let me just do an example of that one really quickly. I didn't do that, I just proved it. So let me say, well, what if this time I have f of x is equal to 3x squared? So this constant multiplier rule says now that the derivative of this is just this number here, sitting here, the constant, times the derivative of x squared, and the derivative of x squared is 2x. So I can just call this 6x. So I'm just writing this out, like you can just multiply these in the first step. You don't have to write it like this, but until you get confident with it, it just means that this 3 just sits here, and then I take the derivative of the x squared, and then I just multiply them together, so I can say my f prime is 6x. Okay, so let's use all of our rules here. So the first case in a lot of these is just to rewrite it so I can use my power rule. So the first thing I'm going to do is rewrite this as 3, and then this will be, I can write this as x to the minus 1. Okay, I'm just pulling up, the implied exponent here is 1, so when I pull it up it becomes a negative exponent. So my y prime, I'm just going to use some different forms of how we mark the derivative. So this is y prime, is how it's said, is 3 times negative 1, because I multiply the exponent down. X to the negative 1 minus 1 gives me negative 2. So in the end, I can simplify this to negative 3 x to the minus 2. There's my no limit process required. All right, so 2, f of x is 4x squared over 5. So I also want to remember that this is the same thing as if I wrote 4/5 x squared. So my f prime of x would be, so the 4/5 stays here, and then the derivative of x squared is 2x. Right, so then I can simplify this in the end and say my f prime of x is equal to, I think of this 2 as 2 over 1, I multiply straight across and I get 8/5 x. And that's my derivative. Okay. So much simpler, right? All right. So I can also use it with radicals because we can write our radicals as an exponent. So my rewrite here is f of x is equal to 2x to the 1/2, right? Power over root, implied power here is 1 as the power, root is implied it's 2, so I end up with a half. So f prime of x is equal to, the constant sits here, and then I multiply the power down, a half. X to the 1/2 minus 1 is negative 1/2. So f prime of x is just x to the negative 1/2 because my 2 times my half becomes 1. All right. All right. My next one here, g, is a little bit more complicated, and so I have 1 over 2 times the cube root of x squared. So I'm going to rewrite this maybe a couple times in baby steps. So first I'm going to write it as x to the 2/3 down here, power over root, and then I need it to come out of the denominator. So my g of x is equal to, the 2 and the x are not attached, right? They're just sitting next to each other. So this is 1/2 x to the negative 2/3. Right? So that gives me g prime of x is equal to 1/2, it sits here. I multiply down the power, negative 2/3, x to the negative 2/3 minus 3/3 is negative 5/3, right? Negative 2/3 minus 1 is x to the negative 5/3. And so I can simplify this a little bit, giving me g prime of x is equal to negative 1/3 x to the negative 5/3, because I get negative 2, 6, so I'm simplifying that all in one step. And then the last example is my negative 3x over 2. Again, I want to think of it like negative 3/2 x. And this is our special case, right? I have x to the first power. And so this is, I want to think of it in terms of, right, this is a constant slope, right, that has a linear function. So my y prime in this case is negative 3/2.